Hello, my name is METİN Arıdaşır. This is 139th part of explanation of my theory. Arıdaşır's main method of determining electrons' velocities which are different from relativistic and classical results. According to my theory and my formulas, 1. For detecting electric potential applied accelerated electron motion forms velocities, we need two values. One of that value is certain wavelength size of electron motion forms, initial at rest wavelength lambda normal. This is the first page that I wrote and drew. Snapshot. I hope you see. And the other is amount of applied voltage. If we know these two values, we can find electron motion forms in the 0 degree direction, in its motion direction, of course, velocity. Yes. Here, we use, for instance, lambda normal is equal to 91.155 nanometer. At rest, electrons' initial wavelength. And our applying voltage on this electron is 30,000 volts. 2. Then, the first step is applying my shortest shortened wavelength of accelerated electron motion form formula. Here. This is first step. I know lambda normal. I know voltage. Then I can find lambda n, lambda normal minus delta lambda is equal to 1238 nanometer volt. This is constant, one of my constant, divided by applied voltage. What is delta lambda? Look at that. You see delta lambda. Okay? Here, delta lambda. We must find this. And lambda minus delta lambda, shortest shortened wavelength in the direction of electron motion forms motion, in the direction of 0 degree. This is first step. Then we find lambda normal minus delta lambda is equal to 0.0416 nanometer. Yes, we managed the first step. This is so important. Then, second step is for determining electron velocity from this real relation. What is relation? Delta lambda divided by lambda n is equal to electron velocity or source velocity divided by speed of light. this relation. This mustn't make you confuse. This is not Doppler relation because this is real shortening. Okay? Not as if shortening, not apparent shortening. Second step is for determining electron velocity from this real relation between lambda normal, delta lambda, speed of light and source of electron motion form velocity. Delta lambda divided by lambda normal is equal to electron motion form divided by c. Okay. We will determine electron motion form at last step through this relation. But before we have second step. Yes, this relation, this delta lambda divided by lambda n is equal to electron motion form's velocity divided by c, or velocity of source divided by c, represents real shortening of wavelength. This is nothing to do with Doppler effect. Okay. Then firstly, second step, we find delta lambda. This is my delta lambda finding formula. Delta lambda is equal to lambda normal minus lambda normal minus delta lambda. Here. Yes. Delta lambda between these. Here. Lambda normal minus delta lambda between these. Totally two of that. Delta lambda plus lambda n minus delta lambda is equal to lambda normal. So, delta lambda is equal to lambda normal minus delta lambda normal minus delta lambda. Easily, finally, we can find delta lambda is equal to 91.155 nanometer minus 0.0416 nanometer is equal to delta lambda is 91.1134 nanometer. Yes, we finished the second step. Now, then, third step. What is 91.155 nanometer wavelength size electron motion form, which is applied on 30,000 volt electric potential? What is its velocity? Here. We put the figures to formula delta lambda divided by lambda normal, electron motion form velocity divided by c. Electron motion form here is 299,863 km per second. Yes, we finished third step. Finally, we found electron motion form's velocity, which is applied on 30,000 volt, which is 91.155 nanometer. Yes, we managed to determine electron motion form's velocity under the influence of a certain amount of voltage, electric potential. There are different kinds of electron motion forms, different size, wavelength size. But for shortened wavelength, only for this 0-degree direction wavelength, lambda normal minus delta lambda is the same for all of this. But same applied voltage, different velocities. But here, this is our example, 91.155 nanometer. Yes, now, here, snapshot. Here, comparison. My theoretical results, relativistic theory results, classical theory results. Okay. Snapshot again. I hope you see. For 30 volts, according to my theory, for 30 volts applied voltage, 163,090 km per second electron gains this velocity. Here, 3,248 km per second relativistic. 3,249 km per second classical theory. So interesting. Wait, please. 50 kilovolts. My computing, my theory, 299,917 km per second. Relativistic theoretical result is, computation is 1,237, 120 km per second. Then this is classical one. For 9 megavolts. This is my computation. This is relativistic computation. This is classical computation. Now